Good morning students. In this class I would like to explain about diagonalization of a matrix. The definition of a diagonalization of a matrix is a square matrix capital A is said to be diagonalizable if there exists another non-singular matrix square matrix P such that P inverse AP is a diagonal matrix. Square matrix capital A, square matrix means rows and columns are equal. Then it is called square matrix, which is said to be diagonalizable if there exists a non-singular matrix. Another matrix P must and should be existed, which is a square matrix such that the result of P inverse AP must and should be a diagonal matrix. What is meant by diagonal matrix? Diagonal matrix means except principal diagonal elements are zeros. That is, the principal diagonal elements at least are non-zeros and the remaining elements must and should be zeros. Such matrix is known as diagonal matrix. Except principal diagonal elements are zeros, then it is called diagonal matrix. In other words, A is a diagonalizable if A is similar to a diagonal matrix. What is a diagonal matrix here? D, capital D. Two matrices A and B are said to be similar matrices if there exists a non-singular matrix P such that B equal to P inverse AP. Then A and B are called similar matrices. This transformation of A to B is known as similarity transformation. Such a transformation is known as similarity transformation. What is the transformation here? B equal to P inverse AP. What is P here? Non-singular matrix. Non-singular matrix means det P is not equal to 0. Determinant of P is not equal to 0. Similar matrices A and B have the same eigenvalues. Further, if X is an eigenvector of A, Y equal to P inverse X is an eigenvector of the matrix B. Now, working rule to find the matrix P, model matrix P. The matrix P is called model matrix of A. There are the following steps to obtain the diagonal form of the matrix A. In step 1, we have to find out all eigenvalues of the matrix A. So here the eigenvalues are represented with lambda 1, lambda 2 and so on, lambda n are the eigenvalues of A. In step 2, if there exists a pair of distinct complex eigenvalues, then A is not diagonalizable over the field or of A. In real number matrices, if A existed, the eigenvalues are complex numbers. In such a case, A is not diagonalizable. So complex eigenvalues whenever occur, A is not diagonalizable. In step 3, if there does not exist a set of n linearly independent eigenvectors, then also A is not diagonalizable. So if there does not exist n linearly independent eigenvectors, then also A is not diagonalizable. In step 4, if there exist n linearly independent eigenvectors, then only A is diagonalizable. So in step 3, if there does not exist any n linearly independent eigenvectors, then A is not diagonalizable. A is diagonalizable if there must and should be existed n linearly independent eigenvectors. So those step 2, step 3 are compulsory. Complex eigenvalues are occurred, then A is not diagonalizable. If there does not occur n independent vectors, then also A is not diagonalizable. So must and should be there existed n linearly independent eigenvectors. So here these are the n linearly independent eigenvectors, that is x1, x2 and so on xn. These are the column matrices. These are the eigenvectors. These are the n linearly independent eigenvectors. With these combinations, we will get the model matrix P. So model matrix P is matrix of x11, x12 and so on x1n as first column, x21, x22 and so on x2n as second column, xn1, xn2 and so on xnn as last column. And the diagonal matrix D is given by P inverse AP. So P inverse AP, the result is must and should be D. What is a D here? Diagonal matrix, which contains the principal diagonal elements as eigenvalues, and the remaining elements must and should be zeros. So does the matrix look like lambda 1, 0, 0, 0, 0 and so on, 0, lambda 2, 0, 0 and so on, 0, 0, 0, 0, 0, last element is lambda n. Thus we will have lambda 1, lambda 2 and so on, lambda n as principal diagonal elements, and except remaining elements must and should be zeros. Such matrix are known as diagonal matrix. So simple steps to get the matrix A as a diagonalizable. The first step, we have to find out eigenvalues. A is does not diagonalizable in step 2 or step 3. If we get step 2 or step 3, A is not diagonalizable. That is, if complex eigenvalues are occurred, A is not diagonalizable. If n linearly independent eigenvectors are not get, then also A is not diagonalizable. Must and should be n linearly independent eigenvectors must and should be occurred. So these are the n eigenvectors, that is x1, x2 and so on xn. With these combinations we can define the model matrix P. If we compute P inverse AP, if we get the result as the diagonal matrix D, then we say that A is diagonalizable. Powers of matrix. Using diagonalization matrix equation, we can get the powers of the matrix A. What is meant by powers of the matrix A? A square, A cube, A power 4 and so on. These are said to be powers of the matrix A. For this, consider D equal to P inverse AP. Just multiplying with D, we will have D into D, that is a D square is P inverse AP into P inverse AP. Just changing the brackets, P inverse A into PP inverse AP. But what is PP inverse? PP inverse is I. Inverse matrix definition, PP inverse is I. So P inverse A, I, AP. But what is A into A? A into A is A square, I into A is A. So we will have A into A square, that is P inverse A square P. Thus we will have D square is P inverse A square P. Similarly, if we proceed like this, D cube means P inverse A cube P. On continuing this process, we will get D power n. D power n is P inverse A power P. Now we can obtain A power n by pre-multiplying by P and post-multiplying with P inverse. That is a P D power n P inverse. So we will get, on simplifying, A power n as result. Thus we will have A power n is P D power n P inverse. A power n is P D power n P inverse. Using this equation we can get the powers of the matrix A, that is A cube, A power 4 and so on. Clearly we can get. Diagonalize the matrix. Matrix of 1, 6, 1, 1, 2, 0, 0, 0, 3. The characteristic equation of A is determinant of A minus lambda I equal to 0 is called characteristic equation of A. So taking the determinant of the given matrix, that is a determinant of 1 minus lambda, 6, 1, 1, 2 minus lambda, 0, 0, 0, 3 minus lambda. That is, which is obtained by subtracting lambda from the principal diagonal elements of the matrix A. The determinant is equated to 0, which gives that lambda plus 1 into lambda minus 3 into lambda minus 4 equal to 0 on simplifying the determinant. So we will get the values of lambda as minus 1, 3, 4. These are called eigenvalues. These are the eigenvalues of the given matrix A. So in first step, we have to find out all the eigenvalues of the matrix A. For each eigenvalue, there corresponds a eigenvector. So here considering lambda equal to -1 as a eigenvalue, and x is the non-zero vector which is satisfying the equation a minus lambda I of x equal to 0 or ax equal to lambda x. That is a minus lambda I of x equal to 0, replacing lambda with -1. That means subtracting the principal diagonal elements of A with -1. So we will get the equivalent matrix like matrix of 2 6 1 1 3 0 0 0 of x1 x2 x3 equal to 0. Now we have to reduce the matrix A to the row echelon form. For this we have to use only row operations, that is interchanging R1 and R2. Next step, R2 goes to R2 minus 2R1. Now R1 goes to R1 minus R2, R3 goes to R3 minus 4R2. Using these steps, so clearly the matrix A becomes row echelon form. The matrix A is reduces as in row echelon form. So here the number of non-zero rows are 2. So rank of A is 2. So r equal to small r equal to 2 and the number of unknowns small n equal to 3. That is n minus r equal to 3 minus 2 equal to 1. Thus we have to assign one arbitrary constant to one variable. Now equating the two matrices, we will have two equations, that is x1 plus 3x2 minus x3 equal to 0 and x3 equal to 0. So here we have to assign one arbitrary constant, that is k. So here we are assigning to the second variable, that is x2 with k. So we will have x1 value is minus 3k while putting x2 as k and x3 as 0 in first equation, that is x1 plus 3x2 minus x3 equal to 0. So thus we will have the eigenvector x1, that is the column matrix x1, x2, x3. x1 is replaced with minus 3k, x2 is replaced with k and x3 is replaced with 0. And taking the common as k, so k into matrix of minus 3, 1, 0. It is the first eigenvector, that is x1. Similarly, we have to find out another eigenvalue, that is lambda equal to 3, corresponding eigenvector x2. What is x2? Column matrix x1, x2, x3. Now for lambda equal to 3, taking a minus lambda I of x equal to 0, just replacing lambda equal to 3, that is the subtracting 3 from the principal diagonal elements of A, which is multiplied with the column matrix x1, x2, x3 and which is equated to 0. That is 0 means null matrix. O 0 0 0. Now equating these two matrices, we will have equations, two equations, assigning the arbitrary constants or equating these fractions. We will have x1 value is 1, x2 is value 1, x3 value is minus 4. Or these can be get by equating the equation to a constant k, x1 equal to k, x2 equal to k, x3 equal to minus 4k. And in general we can take the k value as 1, so that we will get the second eigenvector, that is x2. x2 is a matrix of 1, 1, minus 4. Now for lambda equal to 4, another eigenvalue is lambda equal to 4. So subtracting lambda equal to 4 from the principal diagonal elements, and the matrices is equated to 0. Now interchanging R1 and R2. So we will have the matrix, equivalent matrix is reduces as row echelon form, that is x1 minus 2x2 plus x3 is equal to 0, x3 equal to 0. Now equating these equations to a constant k, or directly we can write the values of unknown values x1, x2, x3. These are the unknown values, x1 is 2, x2 is 1 and x3 is 0. Thus we will get the last eigenvector, that is x3. x3 is a matrix of 2, 1, 0. So these are the eigenvectors x1, x2, x3. With these eigenvectors, we can define the model matrix P. The model matrix P is given by P equal to matrix of minus 3, 1, 2, 1, 1, 1, 0, minus 4, 0. It is the model matrix P. First, we have to verify the P is non-singular or singular. Non-singular means that P is not equal to 0, then P is called non-singular. Consider determinant P, just computing determinant of the matrix P. So we will have minus 20 clearly, which is not equal to 0. Now computing P inverse. So to compute P inverse, we have to define the matrix of cofactors. Now adjoint P is the transpose of the matrix B. Now P inverse, formula for P inverse is adjoint P by det P. So computing P inverse, now diagonalization. D. What is a D here? The formula for D is P inverse AP. Computed P inverse given matrix A and computed the model matrix P, which are substituted here, and taking the multiplication of these three matrices and then simplifying, we will get D. So here D is diagonal matrix, that is matrix of minus 1, 0, 0, 0, 3, 0, 0, 0, 4. So here clearly we can observe the principal diagonal elements are minus 1, 3, 4. And the remaining elements are zeros. So it is the required diagonal matrix D. Hence the matrix, given matrix capital A is diagonalizable. So very easy steps, so simple, we can find A is diagonalizable very easily. Just first we have to find out the eigenvalues of the matrix. The eigenvalues of the matrix A are minus 3, 4. These are the eigenvalues. In next step, we have to find out eigenvectors like this. For lambda equal to minus 1, the eigenvector is matrix of minus 3, 1, 0. For lambda equal to 3, the second eigenvector is x2, that is 1, 1, minus 4. For lambda equal to 4, the corresponding eigenvector is x3, that is 2, 1, 0. These eigenvectors made up with the model matrix P. Now first of all we have to check the P is non-singular or singular. Non-singular means det P is not equal to 0. So computing det P, that means the determinant of P is clearly minus 20, not equal to 0. And we have to find out P inverse. For this we have to take the cofactor matrix and then we have to compute adjoint P, which is a transpose of B. And then we can compute P inverse adjoint P by det P. Clearly here det P is not equal to 0. Substituting above values, so we'll get P inverse. Now diagonalization. For this we have to consider P inverse AP. Just multiplying P inverse A and P, we will get the diagonal matrix. If we do not get diagonal matrix, then A is called not diagonalizable. So clearly the obtained matrix is a diagonal matrix, so that A is diagonalizable. Another problem. Diagonalize the matrix A, matrix of 11, minus 4, minus 7, 7, minus 2, minus 5, 10, minus 4, minus 6, and hence find the power matrix A power 5. First of all, we have to diagonalize the matrix and we have to find out A power 5, power matrix A power 5. For this, we have to consider the characteristic equation, that is the determinant of A minus lambda I equal to 0. So obtaining determinant, just subtracting lambda from the principal diagonal elements of A. Determinant is equated to 0. On simplification, we will get lambda values, that is lambda our values are 0, 1, 2. These are the eigenvalues. The eigenvalues are real and distinct, hence A is diagonalizable. If we get the eigenvalues as complex numbers, A cannot be diagonalizable. So clearly here the eigenvalues of A are real numbers. So clearly A is diagonalizable. Now consider A minus lambda I of x equal to 0. Now using this equation we can obtain the eigenvectors x1, x2, x3. With respect to these eigenvalues, lambda equal to 0, lambda equal to 1, lambda equal to 2. For lambda equal to 0, consider same as above, that is A minus lambda I of x equal to 0. So we will have three equations. Solving these three equations, we will have the first eigenvector, that is x1 is a matrix of 1 1 1. Next, for lambda equal to 1, same as above, that is a minus 1i of x equal to 0, that is subtracting 1 from the principal diagonal elements of a. So equating, we will get three equations. Considering any two equations, in general the first two equations are considered. So we will have the another eigenvector, that is x2 is 1 minus 1 2. Now for lambda equal to 2, x3 equal to minus 2 1 2. Now we will have the linearly independent vectors. These three are linearly independent vectors. These vectors which made up the model matrix P. So thus we will have P inverse. Now we can compute P inverse AP. If we get P inverse AP equal to D, then A is diagonalizable. For this, consider D, that is a D equal to P inverse AP. Multiplying these three matrices, we will get the result as a matrix of 0 0 0 0 1 2 0 0 2. Clearly observing this matrix, the principal diagonal elements are non-zeros and the remaining elements are zeros. It is called a diagonal matrix. Thus, computing P inverse AP, we will get the result as a D, diagonal matrix. Thus, A is diagonalizable. Now we can compute the power matrix A power 5. So we will have the formula A power n is P D power n P inverse. Now using this formula, putting n equal to 5, we will get A power 5, that is a P D power 5 P inverse. Now what is a D power 5? D power 5 is the diagonal matrix, which is a 0 power 5 0 0 0 1 power 5 0 0 0 2 power 5, which is obtained by just taking the powers for the principal diagonals of D. So clearly we will get a D power 5. Now using D power 5 and the model matrix P and whose inverse P inverse, we will get the power matrix A power 5. It is the required the power matrix A power 5. So it is one of the application of the diagonalization. So using diagonalization, we can compute the power matrices also. Power matrices means A power 5, A square, A cube, A power 100, A power lakh, like this. We can compute easily by using the diagonalization. Just we have to use the equation A power n equal to P D power n P inverse. With the help of power matrix, we can compute the power matrices of the given matrix A. The matrix A is not diagonalizable. So characteristic equation is a determinant of A minus lambda I equal to 0. On simplification, we will get eigenvalues. The eigenvalues are minus 1, 2, 2. These are the eigenvalues. Let x be an eigenvector corresponding to lambda equal to 2. So we will have A minus lambda I of x equal to 0, which is the equation to find the eigenvector x. Just replacing lambda equal to 2 on simplification, we will get the equivalent matrix. Now we have to reduce this matrix A to the row echelon form. So for this we have to apply the row operations like this. The last obtained matrix clearly is in row echelon form. So here the rank of the matrix A is 2 and the number of unknowns are 3 here. N minus R is 1. There exists only one linearly independent eigenvector corresponding to lambda equal to 2. Only one independent vector is existed here. Hence there does not exist 3 linearly independent eigenvectors. I have already told in working rule. Here the 3 linearly independent eigenvectors must and should be occurred, then only A is diagonalizable. Here only one linearly independent eigenvector is existed, so that A is not diagonalizable. Thank you.